All right, that is time. I'll take what you have. There you go. Thank you, thank you, thank you. Time's up, guys. Okay, I'm gonna say this one time, and I'm gonna say it as nice as I possibly can. If I give another quiz, and you're talking to your neighbor, or you are looking off of your neighbor's paper, I will promptly drop you from this class. I don't care if you have an A in the class. Doesn't matter what your grade is. All right? Do I get everyone's? All right? Is that clear to everyone? Yes? Your eyes are looking at your neighbors. That's academic dishonesty, and I have zero tolerance for it. This is a quiz. It's a small part of your grade. It's not worth being dropped from the class. All right? Clear? All right. I'm recording this too. All right? So this is on record. All right. Shall we do this real quick? It won't take us long. All right. So I have a picture, a general picture. And since the foot of the ladder is moving away from the wall, okay, I'm going to assign a variable to this. I'm going to call that x. So x is changing, right, as time goes on. The tip of the ladder is going to come down the wall. So since it's changing also, I'll call it y. And the 5 doesn't change, so this thing starts sliding down. Now, that's my general picture. The instant in time we're talking about, the ladder is 5. And did I say, what was it, 3 feet from the, yeah, that's, I can probably draw that a little better. Maybe it looks more like this. 5. If this is 3, then the fact that this is a right triangle, you could solve for this side, that's 4, okay? And I made it nice so that that would work out, okay? And then you can write down what you're given and what you want, and then come up with your equation. So you're given how fast the foot of the ladder is moving away from the wall, and that was given as 2 feet per second, I believe. So the rate at which x is changing with respect to time is 2. So I'm given dx dt, how fast x is changing with respect to time, 2 feet per second. And I want to know how fast the tip of the ladder is coming down the wall at a specific moment in time. So I want to know how fast y is changing with respect to time. And I want that at exactly the moment that the tip of the ladder is 3 feet off the ground, so that means when y is 3, right? I want to know that when this distance here is 3, and that's y, right? So just a quick thought exercise here. Should our answer be positive or negative? Negative. Negative, because x is growing, right? Y is shrinking, so my answer should be a negative answer, right? Okay, so now the equation. I need to somehow look back at my general picture and connect x and y together, but it's a right triangle. So I can say by Pythagorean, x squared plus y squared equals 5 squared, right? And that's an equation that has x and y in it. So now I can differentiate that with respect to time. So derivative of that's 2x dx dt. Derivative of this is 2y dy dt. And derivative of the other side is 0. I know what x is, right? At the moment in time, I know what x is. What's x? 4. And so that's going to become, let me just put it here, 2 times 4. dx dt, I'm given 2. Then plus 2 times now y at the moment in time is 3. And then dy dt is what I'm solving for, equals 0. And then you can just solve that for dy dt. Was it like negative 8/3 or something like that? Yeah. Negative 8/3. Okay, that's it. Negative 8/3 feet per second. Yes?
What we wrote,
it's wrong. It's wrong. 0. 0. No, I'm kidding. I'm kidding. That just sounded fun.
The ladder is moving down at 2.66 feet per second.
Yeah, that's fine.
Okay.
Yeah, you just convert it to a decimal.
Right.
Yeah, that's fine. Was there a problem like that in the homework? Yeah. Something like it, yeah? And that was actually a problem that was in my lecture notes that I chose to skip But I also said that this is that's like a classic problem that everyone does, but I didn't do it. I was hoping you would do it in your homework. All right, we move on. So we are officially starting chapter 3. And the title of chapter 3, I started talking about this last class, but the chapter title for 3 is Inverse Functions, which in reality we're not going to spend a whole lot of time in this section, or in this chapter. I mean, there's going to be some time, but we're just going to kind of take a couple of things that are important out of this section and move on. Our goal is to get to chapter 4 as soon as possible, all right? So we are going to begin this. I told you last time, go back and review exponential and log functions. Today I'm going to do a formal review, but it's going to be fast. I was looking for this. There it is. Okay, so here we go. This all just says this is stuff you should have seen already, but let's kind of look at it again. So exponential functions. All exponential functions look like f of x equals a to the x, where a, we call the base of the exponential function, has to be positive and it can't be 1. Why can't it be 1? Yeah, 1 to any power would still be 1, right? So you'd just be looking at a constant flat line, wouldn't you? So we just eliminate 1 because it's not interesting. It doesn't behave like exponential functions do. And why can't it, why can't it be like negative? Why don't we ever put negative bases? That's a harder question. See, I'm already going to go off on a tangent. Look at me. Why is it, I mean, we can define a function like this.
Well, like, if you did, it'd be a line. It'd be like a squiggly sort of deal.
Why is that okay and that's not? Okay, so if we were to graph this, this would be like 2 to all these different powers, right? So what would, if I were to ask you right now for this one, maybe let's call this G, okay? If I were to ask you right here, what's f of 3? You just plug 3 in, right? You get 8, wouldn't you? But what if I ask you to plug in, let's say, a half? That'd be 2 to the half. What does that really mean? Square root of 2. That's square root of 2, and everything's fine, right? Yes? But what about here? If I do this one, what's g of 3? Well, can you do that? Yeah, you get negative 2 to the 3rd power. That would be negative 8. But what if I try that one? What if I try 1/2 in here? You're going to have the square root of negative 2. And what's wrong with that? Can't do that, right? Imaginary numbers. And so what happens is that if you let your base be a negative number, your function's going to start behaving very strangely, and it's not going to look like what exponential functions look like. In order for them to all look the same, kind of, we need to make sure that the base is positive, all right? Now, when you look at the graph of a function, an exponential function, this is exponential growth. So as you were to, if you were to let x go to infinity, that means if we start going out that direction, our function takes off to infinity. So now with calculus, we can kind of talk about this in terms of limits. The limit as x goes to infinity of this function is infinity, right? Now, what if we take the limit as x goes to negative infinity of this function? Well, now we're going that way, right? And where is this function headed? Asymptotically, it is approaching 0, isn't it? So that's why that limit is 0. Now, this works when we have exponential growth. And what is it about the base that tells you whether or not you have exponential growth or not? That number right there, right? That number that we put right here is always going to be exponential growth if what? Greater than 1. Has to be bigger than 1. So like 2 to the x is going to look like this. 3 to the x is going to look like this, right? What makes it do this? What makes it go the other way? If your base is what? Between 0 and 1, okay? So we have the red one if this base is bigger than 1, and we have the blue one if the base is smaller than 1, let's say like 1/2. So if I say 1/2 to the x, we're going to have this blue one, and that's called exponential decay, all right? So a greater than 1, growth. A less than 1, greater than 0 is going to be decay. And notice that when we have decay, our limits change, don't they? This time, as we go to infinity, as we go out that way, it tapers off to 0. And as we go that way, it takes off to infinity, right? So the limits kind of flip places. Questions? All right, some properties of exponentials that you should remember from college algebra, or even before college algebra. Anytime we have same base, multiply, different exponents, we add the exponents. We've been doing that already, so this isn't that crazy. Anytime you have division, same base, right, different exponents, you subtract. Anytime you have something to a power and then the whole thing to a power, that's when you multiply the two numbers here, two exponents. And anytime we have a product, multiplication raised to a power, we can apply the power to each one. These are all properties of exponents. That look familiar? Okay. That's it. That's your review of exponential functions. Now, after exponential functions, you learn about logarithmic functions. Now, logarithmic functions have a very special property, and that is logarithmic functions are the inverses of the exponential functions. So we have that if you're given an exponential function, f of x equals a to the x, then the inverse of that function will be log base a of x. So that the property of an inverse is that when you put them together, they basically wipe each other out. They undo each other. So I always like to think of functions like car washes. You put a car in, dirty car, comes out clean car, right? So like if this is a machine that takes in a number and spits out something, it like takes in the car, spits out a clean car. This function takes the clean car and takes it back to a dirty car, right? So it kind of like puts all the dirt back where it came from. So log functions, by definition, are the inverses of the exponential functions. Again, every log function has a base, right? And that base, again, has to be bigger than 0 and can't be 1. So the same restrictions we have for exponential, we have for log. Now, when you graph log functions, they look different than exponential functions. And the most important thing to notice, and maybe I should go back and look at the exponential function before I say this. For both of these exponential functions, what is the domain?
0 to all real numbers.
All real numbers. So for the red one, I can plug in any number I want, right? It's going to spit out some number. So exponential functions have as their domain all real numbers. Now, exponential functions have as their range, that's the outputs. Your range of an exponential function is always above 0, right? Greater than 0. You can never get a negative number out of an exponential function. Unless you shift it or something like that. But the basic exponential, your range is domain is everything. Range is only from 0 up, right? But when you get to log functions, those things switch places. So if you look at this log function, its domain is only from 0 to infinity, right? And its range is everything, right? Everything. So see how they switch places? Now, when we look at the graph, notice how these limits would change. Or not change, but look at the limit of this logarithmic function. This log function, as we go to infinity, the function goes to infinity. And that just means that this thing grows, right? It's not very fast, but it grows. Just keeps going up and up and up and up. It's just not real quick, all right? Now, can we talk about the limit as x goes to negative infinity for a log function? Can I ask what happens as we go to negative infinity? No, because I can't put negatives into logs. So I can only go and ask what's happening as we approach 0 from the right. And you can see that as we start to approach 0 from the right side, right, our function starts to dive down to negative infinity. And so we have that relationship. Okay? Now, does anyone know what the base of this red one is? Like you know with the exponential, if the a was bigger than 1, we had growth, and if the a was a fraction, we had decay, right? So for this red one, is that base bigger than 1 or less than 1? That's bigger. How would it look if the base of that log was like 1/2? Look like that. Okay? So that's how they change.
And by base, you're referring to A.
I'm referring to A. I'm referring to this base right here. So let me kind of reiterate that. If this function was the function f of x equals 2 raised to the x, 2 to the x, that would be exponential growth, right? And then its inverse would be log base 2 of x. And it would look like the red one or the blue one? The red one. Okay? Now if this was f of x equals, let's say, 1/4 to the x, that would be decay, exponential decay. And the inverse function would be log base 1/4 of x, and it would look like the blue one. Okay? The thing you really have to understand, or the most important things, I think, are these limits. These limits are going to come into play. So without looking at anything, like going through your notes, if someone gave you an exponential function and said, hey, what's the limit as x goes to infinity, you need to be able to visualize what's going on. Okay? Oh yeah, that's exponential growth. As I go to infinity, the function goes to infinity. So we'll get some practice with this, but I just want to make sure we at least remember kind of what these look like. Okay? Now, on a slightly side note, it's still related to this. I told you in class last time that there was a very special exponential function, right? We talked about that very special one. What was that very special exponential function we talked about last class? E to the x, right? Now, e is really just a number, right? E is like approximately 2.718. And since that is just a number, this is an exponential function, that number is bigger than 1, so this is exponential growth, right? Now, what would be the inverse of this function? Natural log function, right? But technically speaking, that's really the log base e function, right? I mean, it's really log base e. But we write this whenever we want to talk about that one, right? We write that. This one was called the natural exponential function, right? And this one is called the natural log function, right? I tried to explain last class why this was so special. Right at the end of class, I was talking about that. Now, I want you to consider another function. F of x equals 10 to the x. All right? Is that exponential growth or decay? That's growth, right? Okay. What would the inverse of this function be? The log function, log of x. But again, technically, this is really log base what? 10, right? So what I'm trying to point out to you is this. This is all I'm trying to say. In this particular case, we use a special notation for the inverse, right? Natural log. And in this particular case of base being 10, we use a special notation. In both of these notations, the base is not indicated, right? You have to know that natural log means base e, and you have to know that log means base 10. Any other exponential function you ever come up with, your inverse function will always have to be written with the base indicated. So if you do, 4 to the x, this has to be log base 4. If you do, let's say, 5 to the x, right, this has to be log base 5. So I guess the reason why I'm bringing this up is why do these two have special notations, but all the other ones don't? Why do you think that is? Do you have any idea? I don't expect you to know, but
Well, E is a special number.
E is special, right?
That's an exception because it's the only naturally occurring number
That behave that way, right? So do you think we just gave it this notation just because we were like, that's so special, we're just going to give it its own special notation? I mean, that seem reasonable? Yeah? I agree. But how hard would it have been for us to just write it like this, right? And we could have, right? But it's so special, we want that. This one right here, same thing. It's like base 10 was so special, we wanted to give its own notation. But all the other bases, they aren't as special. Yes?
One thing is, with log base 10 of x,
Mhm.
you can do like the scientific notation, it might be a little simpler to, I forgot like all the principles of logs, but like if you have like, I don't know, like 2.56 times 10 to the 23rd or something, you know. You take
It's
the
easier
log-
to, yeah, it's easier to work with it. Now, I'm going to get to that. I'm about to get to that. So, we all agree, these two are very special. For some reason, we give them their own notation. Everything else, not so special, they don't get their own notation. That troubles me, well, that troubled me when I first started teaching, because when I'm teaching logs, the hardest thing is the notation. Like, everyone starts freaking out when they see the log notation. And they can't make connections. And then once you start going and start using natural log and log, it just all seems so weird. To me, it would be better if we just never use this and always use that, and never use this and just always use that. Then all logs just seem to be the same thing. Here's why. Here's why we actually use the special notation. It actually has nothing to do with the fact that this was so special we wanted a special notation. It has to do with the fact that this is used so much in the real sciences that the inverse function is also used a lot. And the base 10 exponential function is used a lot in the real sciences, in engineering and physics, because our number system is base 10, right? If our number system was base 8, then 8 to the x would be the special one. But it's because it's 10 to the x that it's special. So imagine years and years ago, you're doing research and you have to type up this like 300-page paper on the results of your research. And within your paper, you're having to put the natural log function into your paper like, you know, several hundred times. Imagine back in the days of typewriters, all right? So do you all know how to type? How would you do a subscript on a typewriter? Do you all know? So typewriter, you don't know what I'm talking about, right? Okay. Piece of paper, you like roll it in there and they type away. So if you subscript, you actually have to stop typing. You have to do like a little click on the typewriter, and then you'd hit E, then you'd do it back, and then X, and then you continue typing. Imagine having to do that hundreds and hundreds of times within a paper, right? Wouldn't it be easier to just type that? You wouldn't have to stop, would you? Right? So we picked up this notation because it's just faster to type than it is to do this. And same thing with this. This base 10 appeared so many times, we were like, look, come on, let's just do that. And then we all understand it's a 10. So it's really just by the necessity of it appearing so many times and trying to speed things up that we did it. But again, I think it causes too much confusion. Yes?
What do you mean our number system isn't tens? Like that's just how
Our number system is base 10. Well, let's first figure out why it's base 10. Why do y'all think our number system is base 10? Because we have 10 fingers, right? Okay, so what I mean is this. All right, you asked for it, so you get it. We have a little bit of time to kind of talk today about this. All right, so look, when you write the number 342.71, okay, we all have a good idea of what that means because we've been dealing with this our whole lives, right? What this really means, though, is this. Each of these numbers represents some sort of quantity. This first number we say is our ones, right? This is our tens, right? This would be our hundreds. Yes? Oh, hundreds. Yes? And then this would be tenths. And then hundredths, blah, 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 right? Another way to visualize this is this. Let me do it this way. This is how many ones I have, right? This is how many tens I have. This is how many hundreds I have. This is how many tenths I have. And this is how many 100ths I have, right? Still there? Okay, now, another way of writing these, okay, well, let me write those a different way. This is really 10 to the first power, right? This is really 10 squared. This is really 10 to the 0 power. This is really 10 to the negative 1, and this is really 10 to the negative 2, right? So one way I could write this, if I didn't want to use this notation, if I want to use a different notation, I could say, all right, the 3 represents how many 10 to the 2's I have, plus the 4 is how many 10 to the 1's I have, plus the 2 is how many 10 to the 0's I have, plus 7 is, wrong color, 7 is how many 10 to the negative 1's I have, and then finally 1 is the number of 10 to the negative 2's I have. This is a very ugly way of writing the number 342.71, right? It is. What's an easier, more condensed way to write it? That way, right? So we understand that this is just a shorter way of writing that, yes? So each digit, right, if we're in the first digit, this is how many 10 to the 0's we have. We're in the second digit, it's how many 10 to the 1's we have. Yeah? Okay. So I want you to consider something else before I move on. When I say we put a number here, number here, number here, I could have chosen different numbers, right? But I could have only put here what numbers? 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? That's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 options, right? 10 options. So this right here means, yeah, I think that's good enough. That's all I have to say. So now I'd like to, let's consider this number. I'm telling you 43.12 in base 8. I'm writing that in base 8. What is that number? What is that number in base 10? So this really means 4 whats? 4 eighths to the, be careful, first power, right? Plus, this is 3 eighths to the 0 power, plus 1 8 to the negative 1, plus 2 eighths to the negative 2. That make sense? So this is what? 8 to the first power is 8, so this is 32. Plus 8 to the 0 is 1, 3. Plus this is 1/8 times 1, that's an eighth. And then plus that's 1/64, right? 1 over 8 squared. This is 2/64, which is 1/32 when I reduce the fraction. If I add that together, that's what that number means in base 10, right? So it's given to us in base 8, but to convert it to base 10, you do this. Does that kind of make sense? Yeah. Now, when I do this, if I said we were in base 8, could I write this number? Could I, if I told you that's base 8, convert it to base 10, could you? Yes. Why not? I'm seeing no's. Base 8 means you can only use what digits? 0, 1, 2, 3, 4, 5, sorry, 7, right? 0 through 7. You're only allowed to use the digits 0 through 7 if you're in base 8. So that means you can't have a 9. Doesn't make sense, all right? That you follow that? I'm going to go one more. What's this number?
Binary.
What base is that? 2. This is binary. This is the way a computer works. Okay? That's a binary number. All right, so if it's binary, there's only 2, right? There's only two digits allowed, 0 and 1, right? So what does this first one mean? It means 1 times how many numbers in our base? 2 to what power? So remember, this is 0, 1, 2, 3. That's 2 cubed, right? Plus 0 2's to the second, plus 1 2 to the first, plus 1 2 to the 0. Okay, let's see what this is. What's that? 8, 0, 2, 2 zeros, 1, so 1. So what is that? 11. This is the number 11. The number 11 in base 10 is written as the number 1011 in base 2. That make sense? Yes? Okay.
What if you tried to go the other way with your base?
You mean go bigger?
Yeah.
Okay, you get something like hexadecimal. Okay, anyone know hexadecimal?
Now,
Okay, so how many digits did we have here?
2.
We had 2.
Does that mean you can put like 11?
Watch. No, you can't, okay, good question.
You put 11.
Okay, so what if I want to do, let's do base 16. Our digits, we should have 16 digits. There will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You can't use 10 because if you use 10, you might think that's a 1 and a 0, right? So what we do is this. If I go base 16, then here are the digits that are allowed. Okay, I can't go to 10. A, B, C, D. Okay, 1, 2, 3, 4, 9. Wait, no, that's 10, right? 11, 12, 13, 14, 15, 16. There are my 16 digits. Okay? So watch. So watch. What would this be converted from base 16 to base 10? 1, F, A, 2. All right, so what does this first one mean? I have 1, what's our base? 16 to what power? 0, 1, 2, 3, to the third, plus, okay, now you can do it. So F, right? So F is what? 10, 11, 12, 13, 14, 15? Is it going to be 15?
F is 16.
Oh wait, no, it's 15. It's the 16.
It's 15. It's going to be 15 times 16 squared plus A, which is actually 10, right? Right? Yeah, 10. 10, 16 to the first plus 2, what? 16 to the 0, whatever that number is. So this is 16 cubed plus 16 squared times 15 plus 160 plus 2. Whatever that number is, that's the base 10 number, hexadecimal. What's that? Yeah, I don't feel like doing the math, but does that make sense?
Yeah.
So you can have any base you want. You start putting letters in there. All right, so that's, what are we talking about? Why are we talking about this? Oh, because base 10, the base 10 log, right, is special because base 10 is our number system, right? I've always found that amazing. Like if we had 11 fingers, we'd be working in base 11, and base 11 would make perfect sense to us. There's no reason why base 10 is special, other than the fact that we've got 10 fingers. Like, right? If we had 8, we would count everything in base 8, and everything would make sense in base 8. All right.
Like,
Back to what?
If we had 16 fingers, though, like, would we come up with a number that's...
We would use symbols. It would just look, A is a symbol, right? Like this is a symbol,
Yeah.
right? We know it as a number,
Yeah.
but we would probably have another symbol. We probably wouldn't have, like if we would have started with 16 fingers,
So
right?
Like a
We would have this,
number that
we would,
represents all the way up to 16.
that's right. We would have a symbol, whatever it is, you know? No, that's not good. Like I don't know. There it is. I don't know. That would be the symbol that we use for, I don't know, whatever you want. It would be whatever it is that we came up with, right? But it would look like a number to us, just the way the number 2 looks like a number to us. Yeah, it's weird. I agree. All right, so logs, that's what they look like. Limits, blah, blah, blah. Properties of logs. Super crazy properties with logs, right? These, when you're learning in college algebra how to condense and expand log expressions, you have all these important properties. Logs behave in a way that not many things do, all right? This idea here, that when you have log base A of a product, so two things being multiplied, that somehow you can split this up into 2 logs. That's a property of logs. It's very unique about logs. If you have log division inside, you can split it up into 2 logs with subtraction. Do these look familiar? Okay, this property was just insane, but we use this so much in calculus. Do you remember that property right there? if you have log base a of something to a power, so if the argument in here is being raised to a power, logs allow you to actually pull that power out front and put it as a constant being multiplied. Super important. All right, so please be aware of those, that they exist, all right, because I will use them. So this was the whole idea of, okay, well, now that we have the idea of logs, there's this very special one, base e, right? And then its inverse is log base e, but we really write natural log of x because it was hard to use a typewriter. Would you agree it would still be hard today, even with word processors? Does anyone know the shortcut key to do a subscript? I don't either. It still takes a while, right? So it's not easy still. And it's a good thing we just do natural log x and it doesn't matter. All right, some properties of the inverse, okay? And these should ring a bell. If you take natural log of e to the x, again, these kill each other off, and all you get is what's up here just drops out. And if you do it the other way, if you raise e to the natural log of x, so you're composing the two functions together, they kill each other off and you just get the x. We all know e to the 0 is 1. And we all hopefully know that natural log of 1 is 0. And what's natural log of e? Well, it's 1, right? Because it says. But this is actually the property that there's a 1 there. So you're doing natural log with e, and they kill each other off, and all you get is the power up here, which is the 1. That's actually that property right up there. Now, on your calculators, most calculators just have a natural log key, right? They just have a natural log key. Like if I were to ask you right now, what's log base 4 of 9? You don't have a key on your calculator that can do that. Your calculators only come usually with the natural log and then the log key. Is there a question? Yeah?
Well, I have one that did that.
Yeah, there are some that do it. There are, but most of the scientific ones don't. Not scientific, graphing ones, they don't. And the reason they don't, that one will. I believe. It'll allow you to type in a log like with that whatever base you want. But I'll be honest, those calculators are geared more towards people who wouldn't know the following formula. The following formula says that you can do the log of any base log, you can do it by just using the natural log. So if I wanted to do this on my calculator, all I'd have to do is type in natural log of 9 divided by natural log of 4. And that will work for any base. So basically, you only need one key. You only need the natural log key on your calculator. Does that formula look familiar or something? Yes? Yes?
I thought you could also take like just normal log as well. Like
You can. It's amazing. You could actually do this with any log. You could do log x over log a. You could do that. Now, most of the time it appears in a book with natural log. But what's even crazier about it is that you can do any log. So I could do log base b of x over log base b of a. So if you want to do a conversion from log base a of x to something, you can go any log of any base of the x divided by, same base on this log of a, you'll get the same answer. So, yeah, it works both ways. All right. Yeah, okay, we are done. That's our review of exponentials and logs. And a little bit about number systems.
It's really tricky.
I'll show you something. Well, I don't know if we're ready for this, but I can show it to you. A couple of years ago, I was messing around with one of my buddies, one of my colleagues, and I put that equation on the board. And I asked them, when is this true? When does 0.111 forever equal 1?
But it's not base 10.
Yeah, so this can't possibly be true if I'm saying these are both base 10 numbers, right? Like 0.111 forever does not equal 1. We know that, right? But what if I told you that this was a base 2 number and this was base 10? Then would it be true? Okay, well, let's look at 0.111 forever. Let's see what that is in base 2. So base 2, I'm only allowed 2 numbers, right? 0 and 1. Okay, but here's our decimal point, right? So that first one right there means I have 1, 2 raised to what power? To the negative 1. Plus, now I have another 1, but now 2 to the negative 2, right? Do y'all understand what I'm doing with the exponents because I'm on the right side of the decimal? Okay, and then this next one would be another 1, but then 2 to the negative 3 plus 2 to the negative 4, right? So let me see what this is. This is 2 to the negative 1 is really a half plus 1/4 plus 1/8 plus 1/16 plus 1/32, right? Keeps going forever, right? Now we're not ready for this. That's why I said I'm not quite sure we're ready for this. This is a Cal 2 problem. This is called an infinite series. And let's just look at this. Let's say that the distance from this side of the room to that side of the room is 1 unit, okay? 1 unit. Then let's go halfway. So I walk halfway, right? Okay, there. Now I walk 1/4 of the way of the room, right? So 1/4 would take me like another half. And then I go another half of that. And I go another half of that, and another half of that, and then half of that, half of that. And I do it forever. I realize that I will never reach the wall, okay? Because you can't do that forever. But it's converging to the wall. And so this is actually saying this bar over the top says that this equality is true because I will converge to 1. That makes sense? So this decimal in binary is actually equivalent to that number in base 10. Weird, huh?
So, like, if we had a different base counting system, does that mean that, like, if we say, like, $100 now, would that be, like, 400 in, like, base?
Some other base?
Right, because they're different numbers, aren't they?
Yeah, they're
So,
different.
like, any number we would have, I guess, in this, like, universe or whatever, right? Then in another number world, it's like...
It could be something completely different.
It's so weird.
So if there's like intelligent life somewhere else, they have their own base. Is that what you're saying?
Yeah.
Yeah. I mean, yeah. Yeah.
I don't know.
Yeah.
That's so weird.
So in math majors would take courses called like number theory. Number theory, you get into all this sort of things. You get into the bases, you get into primes and all sorts of weird stuff. So, all right. All right, so now we want to talk about the derivatives of, what we have essentially done is said, hey, look, now that you've been reminded about exponential and log functions, what are their derivatives? Okay? I showed you last class that e to the x was super special and that it was its own derivative, right? And it's the only function that does that. But that's not where we're going to start. We're going to start by talking about what's the derivative just of a general exponential function. So if someone were to say, here's the function f of x equals a to the x. Let's say that a is bigger than 0 and a is not 1. So this qualifies as an exponential function. The question is, what is its derivative? I'm not going to prove this to you. I'm just going to give it to you. And you're going to just say, OK, that's what it is. I take it on faith, and then we're going to move on. So the derivative of this is, well, itself, which is actually pretty nice. But there's one thing you have to multiply this by. The natural log of the base itself. And this is kind of our formula. All right, this is kind of the formula we're going to use now. This is on your cheat sheet, or on your formula sheets. This derivative formula is there. Maybe someone can tell me what formula it is. Let's see. It's in our differentiation formulas. Go back. Right here, right here, right here. This is formula 10 on reference page 5. Reference page 5, formula 10. Do y'all see that there? Okay. let's do an example of this. Let's just do an example. As an example, if I say, hey everyone, y is equal to 4 to the x, find y prime, you would tell me it's what? 4 to the x times natural log of 4. Now, natural log of 4 is just a number, isn't it? It's just a number. So if this is a number, what we're really doing is we're taking some number, right, and we're multiplying it times 4 to the x. Agreed? So we're saying that the derivative of 4 to the x is itself, but it's been scaled. Scaling it is either going to like stretch it out or shrink it or something like that, right? So it's like it's almost itself, but it's been stretched or compressed, all right, by that amount. With me? Okay, so now let's do another one. If we do y equals, let's say 1/2 to the x, then the derivative of that would be what? Itself, 1/2 to the x times natural log of 1/2, right? Okay, now let's get to the very special one. If y is equal to e to the x, what is its derivative according to this formula? Itself, e to the x, but then we have to scale it by what? Natural log of e. But what is natural log of e? It's 1, right? That's 1. So this is really just e to the x. So it's the same principle, but the thing you're scaling it by is 1, so it doesn't get scaled at all. It just stays the same. All right? Okay, let's do a couple more. I'll leave that up on the board. How about this? What was I going to do? I forgot. What the hell was I going to do? I wanted to show you another example. Hold on. Oh, yeah, no, I was going to show you what I'm going to show you a mistake, so don't write this down. I'm going to do it in red. Don't write this down. Okay, so here's my student taking the test. I'm sitting there in my living room, chilling, grading the test, right? Student gets that. They take the derivative. You see what they did, right? You see what they did? They applied a power rule. They applied the power rule, didn't they? They brought the power out and subtracted 1 from the power. I kick the dog that walks by. I kick the dog. I get all upset because they fundamentally don't get this, right? There's a huge difference between that and this, right? So here, this is a power function. The variable x is in the base. The fixed number is the power. The derivative of this is 4x cubed. Here, they switch places, right? The variable is now in the exponent. The fixed number is the base. That's an exponential function, and the derivative is not this, right? So I should say, this is correct, okay? That's correct. This is not, right? The correct answer, we just put this on the board a second ago, is this. Right? Okay. Don't make me beat up my dog, okay? My wife's dogs, I should say. I can just see some news report, a professor gets arrested for animal cruelty, talking about, no, I don't think that'll happen. That won't happen, right? I spent like $500 on that stupid dog the other day because he didn't feel right. Animals. All right, you ready? Got another one for you. You get the idea? Uh-oh. What's the derivative of 4 raised to the sine x? Any ideas of what we're going to need to use here? Chain rule. Chain rule. Chain rule, right? So this is layered again. Remember the chain rule, the way it worked is we kind of worked from the inside out, right? We started with the outer function and worked our way in. The outer function here is the 4 raised to something. And there was a way we could remember what the outer function is, and that's to like just plug a value in for x. If I plugged in a value here, the first thing I would do is do sine of it, right? And then I would take 4 and raise it to that power. So 4 to that power is the last thing happening, so that's the first thing you have to take the derivative of. So what would be the derivative of 4 raised to my hand? 4 raised to my hand, right, itself, times the natural log of 4. Don't forget that part because that's part of this formula. Okay, so what I've done is I've kind of fulfilled this part, but I'm not done. Chain rule says now multiply by the derivative of sine of x, which is cosine x. You'll see how that works? Let's do another one. I'm just going to erase this because you've already memorized that, right?
So if it were x squared,
If it were what? Sine of x squared?
you'd have to add another.
Yep, so let's do that. 4 raised to the sine of x squared. Okay, if we wanted to do that, the derivative of this would be, well, first the derivative of this is itself, right? Times ln of 4. Okay, that's going to come every single time. Now you can start working with the top, or the exponent. Derivative of sine of x squared is cosine of x squared. But then chain rule, you still have to go inside the sine to the derivative of x squared, which is 2x. And be careful, you can't do 4 times 2 is 8, right? You can't do that. Because this 4 is being raised to a power. You can't combine it with the 2. Yeah? Okay, how about this then? Another one. We'll start it over here. How about this? Y is equal to x to the 4th times 4 to the x. Product rule first, right? You have a product rule right there. So the derivative will have to be derivative of this one, which is 4x cubed times 4 to the x. Then plus derivative of 4 raised to the x, which is itself times natural log of 4. And then times the x to the 4th, which finishes off our product rule. Questions on that one? F prime g plus g prime f. Just want to see how these derivatives in here look. Yeah. One more. I want us to take derivative of this. All right. So what do you see happening here? I know it looks terrible, but it's not as bad as it looks. What's that? Quotient rule, right? So maybe I'll write the quotient rule out with the little prime marks just to get us all in order first. I'm going to take the top, and I'm going to take its derivative, right? Times the bottom. and then minus the derivative of the bottom times the top all over the bottom squared. That looks easy, doesn't it? No. All right, let's do it. Derivative of this, right? You have addition, so you derivative of each one separately. What is the derivative of e to the x? Just itself, e to the x. Okay. I'm not going to put anything next. It's going to be plus, right? But what's the derivative of e to the negative x? Be real careful here. Think it through. It's itself, right? E to the negative x, but then times what? Negative 1. Where's that negative 1 coming from? The derivative of that, right? Chain rule. So if I ask you to take derivative of e to the negative x, it's itself times the derivative what's up here, which is negative 1. Okay, now we didn't have that happen on the first one, did we? Because derivative e to the x, we actually, if we did chain rule, it would still work, right? Because it would be itself, and then what's derivative of x? 1, right? So it's there, but we don't need it. Also, I'm not putting natural log of e. Why? It's always 1, right? So anytime I take derivative of e to the x, I don't worry about that natural log of e thing. It's just, it's there, but it's gone. Okay, so what's the next piece here? Minus e to the negative x. And now I have to write that one again. E to the x minus e to the negative x. And then minus, now let's do this derivative. Derivative of that is just itself, e to the x. But now, yeah, this minus, I'm just going to cover it. The derivative of this is, again, negative e to the negative x. But then I have a negative there already, right? So plus e to the negative x. And then times the last piece, e to the x plus e to the negative x. Whoa. All over e to the x minus e to the negative x squared. Yeah, that's the derivative. This is the same thing. So it's really this squared, isn't it? But that's this, isn't it? Isn't that? So like these two together would be e to the x minus e to the negative x, that quantity squared, right? That's what those two together would be. And then these two together would be e to the x plus e to the negative x squared. So if I split this into two fractions, I did this over this minus this over this. I could do that, right? So if I did this over that, what would I get? 1. So I get 1 minus, because there's a minus here, and now this over this, right? Those aren't the same. This one has a plus, this one has a minus, right? But they're both squared, aren't they? So I could, if I want, write this. E to the x plus e to the negative x over e to the x minus e to the negative x, all of that squared. Couldn't I? I could. That's y prime. Does anyone recognize what's in parentheses? That's my original function, isn't it? Now we're done, okay? This is the derivative. We're done. But I just want to show you one last thing. Isn't that what we're saying? 1 minus the original function was y, right? 1 minus y squared is equal to y